Now that we're ready to talk about nuclear chemistry, one of the things that we need to do is look at the nucleus a little bit closer. So when we look at the nucleus for an atom, we've talked about how we have electrons in a cloud sort of outside of the nucleus, and inside of the nucleus we have protons and neutrons. So this is where the vast majority of the mass for the atom is. And most of the time in the past, all we've paid attention to is the number of each of these things. And we have mostly only talked about neutrons when we talked about the total atomic mass. So I'm going to remind you of a couple of things about the atoms. And the first of those is some of the masses of our particles. So remember that our neutron has a mass of about 1.67493 times 10 to the minus 27 kilograms, so that's pretty small. And the proton is almost exactly the same, but a little bit smaller, 1.67262 times 10 to the minus 27 kilograms. And then an electron has an even smaller mass. It's about 1,000 times smaller, and that's 9.10939 times 10 to the minus 31 kilograms. Okay, so we've got our masses of all of these particles. And let's think about a fairly simple atom. And let's actually think about the alpha particle, because then we don't have to worry about the electrons. So an alpha particle is a helium nucleus. And it's a standard helium nucleus. So that means that it has 2 protons and 2 neutrons. So we would write the symbol for it, helium-4 2. This should look familiar from isotope notation. So remember, this is A, the mass number, and this is Z, which is the charge number. Formerly, we have only called it the atomic mass, or excuse me, the atomic number. So this is our atomic number. And we can go ahead and continue thinking about this, but we also want to think about this in terms of charge number, because we're going to use a very similar notation to talk about electrons as well in a little bit. And electrons, of course, don't have any protons, but they do have charge. And so that's why we're going to go ahead and continue to use the isotope notation to talk about all of our different atomic particles. So we'll talk more about that in a little bit when we talk about balancing nuclear equations. For right now, we're going to talk about the masses involved in the nuclei and in changes in the nuclei. So what I want to draw your attention to is thinking about the mass of this helium nucleus. So the the alpha particle, I'll change the notation here. We'll make it alpha, just so we can be clear that this is a helium nucleus, not the whole atom. All right, so this has a mass that can be measured, and it turns out to be 6.64466 times 10 to the minus 27 kilograms. So this is the mass of an alpha particle by itself. So in the alpha particle, we said we have 2 protons and 2 neutrons. So let's add up the masses of 2 protons and 2 neutrons from these masses over here. So we have 1.67262 times 10 to the minus 27. We're going to multiply that by 2. And then the same thing for the mass of the neutron, 1.67493 times 10 to the minus 27 kilograms. And if we add these together, then what we get is 6.69510 times 10 to the minus 27 kilograms. So just to review, in an alpha particle, there's 2 protons and 2 neutrons, and here's its mass. But the mass of 2 protons and 2 neutrons is a little bit higher than the mass of an alpha particle. These protons and neutrons, these are separate. They're just hanging out by themselves. This alpha particle is with those protons and neutrons incorporated into a nucleus. So the difference between these two is called the mass defect. It's not really a defect. I would say it's actually a feature. So this change in mass, this difference in the mass between 6.69510 and 6.64466 times 10 to the minus 27, if we look at how big that is, it's pretty small, right? Our mass difference is 5.045 times 10 to the minus 29 kilograms. So this is technically called that mass defect for an alpha particle. So what's going on? Why is there a difference in the mass between these two? So the deal is that some mass gets converted into energy when these bind together. And there are energies called the nuclear strong force. There's also a nuclear weak force. And this nuclear strong force holds nuclei together. And it's very strong, but it only acts over a very, very short distance, like the radius of a nucleus. So super, super tiny. And if you think about the need for some binding energy, think about those protons. These guys are positively charged. Neutrons are neutral. But we're about to take these guys and pack them into a space that's super, super tight. The size of a nucleus is extremely, extremely small. I don't even have an analogy to help you figure out how small a nucleus is. But anyway, these particles are packed super, super tight together. And so our protons are both positively charged, and we know that positively charged things repel each other. And so although the neutrons kind of form some amount of buffering between those protons, we still have positive charges repelling each other. So this nuclear strong force, this binding energy, squishes these particles together and gets them to attract with each other and stick together, even though we have some positive charges repelling each other at the same time. So the amount of this energy, the amount of energy that gets converted, this can be calculated using Einstein's famous equation E equals mc squared. Maybe you've always wondered when you were going to get to actually use this equation. Well, the answer is right now. So we can take this amount of mass and figure out how much energy was converted by just multiplying it by the speed of light squared. So we have 5.045 times 10 to the minus 29 kilograms. And then the speed of light is 2.998 times 10 to the 8 meters per second. And we're going to square that. And this is just a reminder that kilograms meters squared over second squared is the same as the unit joule. And so this is our energy unit that comes right out of it. So the energy that you calculate from this is 4.534 times 10 to the minus 12 joules. Now this might not seem like very much energy, but just to remind you, this is for one alpha particle, so one helium nucleus. And if we think about light, we've calculated light energy, and if you remember that UV light for a photon has energy that's on the order of 10 to the minus 18 joules, which is 10 to the 6 times smaller than 1 binding energy for the nucleus. So this is actually a pretty big energy value if we think about scaling these in terms of moles especially. So if we convert this into moles, so energy in kilojoules per mole, we can do that by taking this number and multiplying it by a mole. So if we have not just one alpha particle, but a mole of alpha particles, we're going to multiply by 6 times 6.022, sorry, times 10 to the 23rd alpha particles per mole. And we'll go ahead and convert that into kilojoules at the same time. And this is going to get us 2.730 times 10 to the 9 kilojoules per mole. So this is for my alpha particles binding energy. And remember that the chemical bond holding something like hydrogen together, so this is a nuclear binding energy, and this is a chemical bond holding hydrogen together. This is 436 kilojoules per mole. So you can see that chemical bonds hold a lot less energy than nuclear reactions do, nuclear binding energies do. So anytime we use chemical energy to produce electricity, for example, we're going to have a much smaller amount of energy that's available if we're using a chemical reaction to generate electricity. So let's look at a comparison here. So if we think about coal and burning that for some electricity, we can calculate how much energy is released by this reaction. We can actually just look it up because this is also the formation energy for carbon dioxide. And that's going to be 39. Oh, excuse me. I got my eyeball missing one decimal. There we go. Minus 393.5 kilojoules per mole. 1 mole carbon, that's about 12 grams. Then we release 393.5 kilojoules. So what might happen if we release some mass defect energy? We're going to find out by looking at some scenarios that involve actual nuclear reactions. So hopefully you're getting the idea, though, that nuclear reactions involve a lot more energy than chemical reactions do. So let's look at a couple of nuclear reactions. I know we haven't talked about balancing nuclear reactions yet, but we'll go ahead and look at some, and then we'll talk about what the big idea is between actually balancing them. Let's take a look at one of the nuclear reactions that is actually used to produce energy. So we know for sure that that energy is an important product here. And this is one of the ones that's involved in fission. So remember how Otto Hahn had written to Lisa Meitner to talk about why the barium was showing up in his reaction? Well, let's look at that reaction. So we had some U-235, which is one of the isotopes of uranium, and Hahn was bombarding the uranium with neutrons. So neutrons have a mass of 1 and no charge. So in this process, the neutron destabilized that uranium the way that Lisa Meitner was imagining it and having it split into 2 parts. So it would split into a barium isotope, perhaps 141. And barium is element 56, and maybe a krypton, 92. And then, as we'll soon see, we need 3 neutrons as well to finish balancing out the mass here. But if we look at the mass defect between our reactants over here and our products, we'll find out that we get a decent amount of energy that would be released in this reaction. So let's find out what those masses are. So of course we have the neutron. We already know that our neutron's mass is 1.67493 times 10 to the minus 27 kilograms. But we need to be able to find the uranium's mass too, and not all of these are going to just be available in your textbook, so let's go look them up. One of the places where we can find out information about isotope masses is on Wikipedia. As I said, Wikipedia has a lot of useful information for scientists. So you can see there's a lot of different isotopes here. So let's scroll down to the one we want, U-235. All right. So, we've got a couple of different crazy pieces of information here. That's okay, because this is the mass that we need. We don't need it in energy. We want it, well, I mean, we could, but we're not ready to go to energy yet. So instead, we're just going to go ahead and use this mass. But this mass is in atomic mass units or in grams per mole. So we need to be able to convert it into a unit that we can actually handle, which is going to be kilograms. So we have 235.0439299. Let's go ahead and do that unit conversion. So 235.0439. What happened there? 299 grams per mole, and we need this in kilograms. So what we need to remember is that 1 mole of uranium contains 6.022 times 10 to the 23rd atoms of uranium, and we want kilograms per single atom. So we're actually limited right here to only 4 significant digits on this Avogadro's number value, so let's actually go find a better value. Okay, if you search for a better value with more significant digits, for most constants you can find them, and sure enough I did. So I'm going to go ahead and add those extra 4 decimal places here. So we have 4 more significant digits to add, and that will make it better for us when we're doing our calculations. So the way that we are going to do this unit conversion is we want to cancel out the moles. So that means we're going to have 1 mole on the top and 6.0221409 times 10 to the 23 on the bottom. This will get us grams per atom. So that's the mass of 1 atom. But we want kilograms, so we also need to divide by 1,000. All right, so if we do that, we will get 3.9029961 times 10 to the minus 25 kilograms. So the total mass on the reactant side is going to be the sum of these two numbers, our neutron and our U-235 mass. So together, that means that the mass of the reactants is going to be 3.9197454 times 10 to the minus 25 kilograms. So we want to do the same thing on our products side. So our products, we have that barium-141, if you look up the mass of that isotope, and then do the unit conversion like we just did. That will, let's see, here's my barium. That will be 2.3399386 times 10 to the minus 25 kilograms. The krypton turns out to be 1.5264697 times 10 to the minus 25 kilograms. And then we have 3 neutrons. And so I'm not going to write those in. I'm just going to put times 3, 1.67493 times 10 to the minus 27 kilograms. And when we add all of these up, we get 3.916656 times 10 to the minus 25 kilograms. So we're talking about mass defects here, right? So we really want to look at what the difference is between this mass and this mass. And you can see by looking at them that they are different starting in our third decimal place. So we're going to actually have a pretty big mass difference here, relatively speaking. So I calculated that mass difference to be 3.0888 times 10 to the minus 28 kilograms. So when we calculate that energy difference from this mass defect, and I'm going to go ahead and be lazy right now and just use the speed of light of 2.998 times 10 to the 8th meters per second, which will leave us with only 4 significant digits, but that's still kind of decent for a ballpark number anyway. And we get 2.776 times 10 to the minus 11 joules. So let's review very quickly what kind of a mass defect and energy we got last time. So when we were looking at helium, it was an alpha particle. So our alpha particle versus 2 protons and 2 neutrons. We got an energy difference from this mass defect of forming the alpha particle of 4.534 times 10 to the minus 12 joules. So this is a significantly bigger amount of energy, and it shouldn't be too surprising then that this reaction is one that is used for producing electricity. So I'll put a couple of other reactions up here if you want to go ahead and practice on your own. These are also fission reactions. So they are involving U-235, which will be nice because then you don't have to look up the mass of that isotope again. And in fact, the reactant side is going to stay the same because all 3 of these are going to be reactions where we bombard our U-235 with a neutron. So it doesn't have to break off into barium. It can also break off into tellurium. In fact, there's lots and lots of different options. And a different krypton isotope. I see a problem here. My previous, okay, I wrote down this reaction, but I didn't actually check the mass number there. So I had written down 92 on the krypton, which is okay, but 36 is not its mass number. Let's go and check this out. Okay, phew, krypton is krypton 36. So that means that I probably just wrote down the wrong one. And yes, okay, that makes good sense. I wrote down krypton instead of zircon for that 40, so let's go fix it. All right, so remember that the number of protons determines our atom type. So this was zircon, and so we don't have to recalculate our previous energy. Phew, okay. I hope I copied this other one correctly. So this one is also U-235 and a neutron. But this time we are making cesium-138 and rubidium-96. So if you would like, you can practice calculating your mass defect for these 2 other reactions, and also, not that energy, but the total amount of energy that would be released from these reactions for a little bit more practice for calculating the mass defect. Otherwise, I hope that you feel pretty confident. The mass calculations are pretty straightforward. The main challenge here is simply figuring out what the mass is in kilograms, and that's just a little bit of dimensional analysis.